The first workshop, we're just going to talk specifically about the project. And then in the next workshop, we're going to go big picture, talk about the challenges of generally building in the global south. And we're going to kind of bring in a little bit of my own experience in Sudan, not just the project in Tanzania. So for the project itself, we have 3 agendas. First, we're going to talk about what comfort is, because that's a big theme of this workshop. We're going to talk a bit about the project itself and how we optimize the design. And finally, we're going to do a thermal comfort analysis. We're going to use 4 different metrics just to kind of cover all the different ways people count something as comfortable or not, because it's a big part of the discussion. So first, what is comfort? The Elsherif states it's a condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. So the first key is a condition of mind, and that's a key part of why defining it is not as simple as people think it is. Like, it's not a number that you can give people, this is what you're going to be comfortable with. There's 2 kind of schools of thought that look at this, and they both kind of derived into different design techniques, different ways of looking at buildings and mechanical ventilation, mechanical systems. So first is the predicted mean vote method, and then there's the adaptive method. So the key fundamental difference between the 2 methods is the PMV sees comfort as something physical, something you can measure, something that we have these particular parameters: heat conduction, metabolism, air speed, air temperature, humidity, and then you put it in a formula and you get a number out. And they use that using climate chamber studies that were done in the 1970s. Now, the adaptive method is a more recent method, and it's becoming a bit more adopted, which it considers the human part of it. That actually there is human adaptation, there's behavioral adaptation, physiological and psychological. Now, I've highlighted physiological because it's a contentious point. Some people think, no, it's entirely psychological, but no, there are physiological changes that your body makes to make you comfortable in a different temperature. So in the PMV method, to them, comfort is a very specific range that is defined regardless of what time it is, who you are, what day it is. This is what comfort is. With the adaptive method, it perceives comfort as something that is different based on region and time. You, as the same person, might be comfortable at a temperature in summer, but you won't be in winter in that exact same temperature. And the same goes to acclimatization. Someone in a hot climate will be more comfortable with hotter temperatures than someone who's used to colder climates. And there's even evidence of short-term adaptation and long-term adaptation. So the PMV method is generally advocated by HVAC engineers. Why? Because they have a physics background. They're used to numbers. They want clear, standardized ways for designing and sizing their equipment. Whereas the adaptive method is more advocated by architects who prefer passive solutions, natural ventilation. And when you're dealing with natural ventilation, you're dealing with the elements. You're dealing with something that is not as consistent and stable as it is with the mechanical. So this is the Elsherif Standard 55, and it's one of the standards that has accepted both methods as valid. And I'll give you an example here. So the temperature 28, if you use the PMV method, it will tell you, using all the same parameters, that it's not comfortable. But if you use the adaptive thermal comfort model, it'll tell you, yes, it's comfortable if during that day the mean outdoor temperature was 24, 25. So this is just an example of how different. And you can see here how small that range is compared to how much this range considered is comfortable. So why is this important, and why is it relevant to sustainable buildings? Because you need to build habitable buildings. You can't, for example, put no heating in a building and say, oh, well, it's saving energy because, well, there's no heating. So you have to make them habitable. And what that definition is a key part of it, and it has a huge impact. So there was a recent study about something called dynamic set points, where instead of having the same set point the entire year, you just change it based on what temperature it is outside, and it has done massive savings in energy building. So it's a huge part of energy savings. So we're going to talk a little bit about the case study.
Okay, so Kamran, I should introduce Kamran. He got us involved in this. This is your baby in a way, isn't it? Eco Village in Tanzania, a sort of permaculture-based community project. And we were asked to review some of the existing buildings, which weren't functioning very well for various reasons. And then we were asked to, my business partner and I, Huda Elsherif, to propose a different way of going about it. And the brief was basically for a 10-child accommodation with an in-house mother. So it's a large house. So one of the first things we did was to anticipate in the final design. We developed a small version of it. It didn't look anything like the final building, but it was a small test unit that took all the features we were hoping to check whether they would work or not. And basically fill it full of data loggers, have the building used for 12 months and try to understand, did our ideas work? Our ideas were based on precedent. We didn't invent stuff. We looked around, best practice, inspirational architects and builders. So this is the Eco Village site. How many acres is it? 30 acres. This is the boundary of the site. It's in a sort of, you could say, rapidly urbanizing village settlement, towns, but maybe 20, 30 years that could look very urban, maybe even sooner, actually. North is that way. The village has built an eco-mosque here. The test unit is here. These are the existing houses, and this is where the 5 new houses are destined for. We've just now completed that one. So back to the test unit. Next slide. And that's to you.
Yep. Okay, so Tanzania, if you look at, this is from the Passivhaus classification, it's around this area, and you can see there's a lot of different colors. There's hot, there's warm, there's very hot, but once you enter into PHPP, it's like very hot. So in a hot climate context, so these are the parameters from the PMV, the parameters that it defines comfort from. And in a hot climate, we need to focus on increasing the airspeed, and the reason that helps, it helps because it lets you sweat faster and easier. And so you become more comfortable in cooling, but it doesn't do anything to the building itself. Next, we have that, which again is linked, is the humidity. If we can, as much as possible, let the air flow, because you don't want that humidity to build up, and because the higher the humidity, the less you're comfortable with the exact same temperature. We're going to try to reduce, we wanted to reduce the air temperatures, mainly by using shading. And we wanted to reduce the radiant temperature. So what the difference between the air and the radiant temperature is, the air is what's around you, but the radiant temperature is coming directly from the sun. And in this tropical environment, it hits the roof in particular, which is what our focus was. And you can impact the radiant temperature a lot more than the air temperature, because with the radiant temperature, just shading has a huge impact. But with air temperatures, it's less of an impact, and you need active cooling, or if it's a hot climate, evaporative cooling to actually change the air temperature. You can talk.
So the original concept that me, Adele, and Alan Clark were discussing was, what are we actually aiming for? And we spent a lot of time learning about the Eco Village and sitting under this cashew tree here, which is the village square. And basically the conditions there were very pleasant. There was access to wind, cooling wind, plenty of shade, and good light. And we thought, well, that's actually what we're aiming for. So in a way, that was our technical brief. Right, okay, so basic concept. So the ideas we wanted to apply to the larger house, we packaged down into what we hoped would be a test unit that was also a useful building. Now, that had some problems doing that. So basically, there were 2 guest bedrooms and a male and female toilets. So basically, it's a cube. So the key features we tested were a highly reflective roof, fully ventilated, no soffits, no gables. Well, come back to that, and a split ridge. The idea being that we could allow air to move through it, and any hot air would tend to rise up through this and move upwards while fresh air came in there. So ventilated roof design. We were aware of the need for cross ventilation across occupants to cool their bodies, just as Huda's talked about. So we had basically windows and doors not on opposite sides of the wall of the rooms, which would have been better to test it. So that was a slight compromise because we're trying to make it a useful building. Everything was insect mesh protected because there's quite a lot of mosquitoes in that area. And then we relied on active cooling through fans. So ceiling fans was another key feature. So in terms of like air movement across the room, we had 3 ways of doing it in this original design. We wanted some trickle ventilation that would always be present. This is a ventilated window seat, and we had the main windows and also holes in the ceiling. And the idea was that would create a stack effect in still days and would allow in windier days for air to move across the room, across the occupants and out. That was the result of 12 months data logging. Are you talking about this?
Yeah.
Yeah.
So the results showed that, so this is the house that they monitored that was built already on the site, and this is the test unit. And you can see there is a reduction, particularly in the peak. It went from 34 to 30. But we felt that in the new designs, that they're going to bring those designs, but they wanted to optimize it a bit more. So this is the main house. And they took a lot of those similar concepts, but one thing that they did is they first removed the glass in the window, so it became completely open, but also in between the walls, they've added these ventilated blocks. So now the air could flow through the entire building.
Just to be clear about that glass, the original build test unit was designed not to have glass, but the wooden louver shutters were misinterpreted by the builder to be a standard glass louver system. So it did end up being glass, but they were louvered system. Okay. Yeah.
So these are the windows, and they were designed a bit triangular to kind of guide the air into the building. So this is what the building looks like. You can see those triangular windows, the open ridge over here. This is the living area with the big doors, and here it's open, and both sides were in the initial design open. Now, why, if it worked pretty well, so why would we want to improve it in more? Because in indoor thermal environments, even just 1 degree of cooling makes a big impact. And so any design optimization you could do helps, especially with climate change. So the strategy that we took, because the building was already kind of half built, so we could monitor what was already going on. And also we have a CFD model, which is just a thermal computer model of the design. And we can see how the airflow works and optimize, and then see how that's working on site. And it helps to mesh the two together, because a model is only as good as the data you have. And using real life data really helped optimize and make sure that that model is accurate, because what we hope is that we optimize this design so that the other units become based on that optimization. So first we need to calibrate that model to make sure that it actually works. And as you can see, they very much closely match. It's never going to be an exact match because the weather data in the model is not exact to the actual data happening, but it shows that it very much reflects what's happening. So in the initial design of this unit, there's ceiling openings here, and both sides were opening. And we wanted to make sure that, is that actually working? So the 2 questions that we wanted to solve was, do we keep both openings, or do we let one closed, or do we keep these ceiling vents open? And first question is ceiling openings. We wanted to make sure, are they actually helping? Because there's kind of 2 forces at work here. That roof is very, very hot, and it's going to heat that space, and that heat might seep into the living space here. But at the same time, once you open it, you can clearly show here that area starts to become less red, that heat is actually escaping up. So we played around until we found like a width that really helped. And you can see also it significantly helped with wind flow. So over here, where is it? Yeah. So this is the original design that we have, and this is when I closed the openings, and you can see there's a lot more wind flowing through once you
the middle one is where the gables were closed, isn't it?
Yeah.
So, yeah.
Yeah, when we closed there.
Yeah.
So you can see it here a bit more. So opening it and close it, you can see the difference. And this is what it looks like in real life. In our design, we optimized that it should be about till here closed, but this was a construction error, which is one of the challenges, again, of building in developing countries, that communication, and just generally, it's really hard to get good quality building, and it's something we're going to be discussing in the other workshop. So this was the second design choice. Do we leave this open or do we close it? Because as I mentioned, it's a delicate balance between the radiance and the air temperature. Is it letting in too much hot air? Is the air actually going out?
And one of the practical things about that, if you just go back to that slide, so there are two modes: no sun, still humid weather, where we'll be relying on stack effect to help pull air through the windows and past your body and up and out. And then another one where there's a strong wind blowing, and it's a pressure differential from the front of the house to the back of the house, which will suck air through more powerfully, which is obviously a good mode. What we didn't want, what we weren't sure about, is what was the balance, and if wind was blowing through that roof, would it actually come down the rooms? You know, you've got toilets involved in this as well.
Yeah. So the only way to really answer these questions is, again, using that CFD modeling. And you can see here I designed it closed, one side closed, one side open, and here I designed them with both of them closed. And you can see here the rooms, this is the temperatures in the rooms. The rooms are a lot cooler once those ends are closed. So it shows that actually those two openings on the side were letting in a lot of hot air. And another interesting thing is once we close those two sides, because the exit for the air was smaller, it had a higher pressure, it actually drove a lot more wind flow through the building. And so we chose the decision to close the gable. Right now, the occupants are going to be moving in, and we're waiting to see their input on the conditions, because we think it's a big part of knowing what they think rather than just rely on numbers. So here is the thermal comfort analysis, and we're going to be using 4 metrics. So this is just a general overview of the temperatures, which includes the exterior temperatures. You can see they can get as high as 39 degrees. And the coolest it got was 21. So it's quite a big range, which you wouldn't really expect in a hot, humid climate. You expect like it'd be a smaller range, but that's the temperatures.
There wasn't
that we're
much
working
access to nighttime cooling. And,
Yeah.
and what this graph is also showing is that, you know, generally are the rooms ever hotter than outside, or are they significantly cooler? And do they maximise cooling at the lower temperatures at the night time? So the first test unit had a lot of thermal mass, too much thermal mass, and it was holding on to the heat too far into the night, which made going to bed uncomfortable. So we reduced thermal mass through a variety of design measures. One of the reasons the windows got bigger. Cut out thermal mass, so we just reduced that holding onto the heat into the night, and that has worked, that design decision. And you can see that the ventilated reflective roof does keep room temperatures significantly lower than external ambient. Yeah.
So our first measure that we measured against was Passivhaus. So Passivhaus says that the temperature must not exceed 25 degrees more than 10% of the time, and it gives you kind of like a basic recommendations for U values and glazing types for very hot and hot climates. So that target was not met. So you can see in most of these rooms, we exceeded that 10% threshold, mostly because the external ambient temperature also usually exceeds that threshold. And because we're not using any air conditioning, we're not using active cooling. So does this mean the building is uncomfortable? So let's measure other metrics. So the first metric is our own design target. We wanted to reduce the percentage of hours that it was above 28. And that was just like a starting point, a number that is relatively comfortable. And you can see that for the cooler months, we didn't exceed that. But for so March and April are the hottest month, and our highest exceedance was 36% in the second bedroom. So it's a massive reduction from our previous design. Let's go back. The adaptive thermal comfort. So the adaptive thermal comfort asks you, are you comfortable at this temperature based on what is the temperature outside? Because it assumes that you have a contact with the outdoors, that you're not in a sealed environment, that you go outside, and especially in our case because they are exposed to the outdoor temperatures. And as you can see, most of our temperatures are actually within that comfortable zone. It's 98 to 99% comfortable. Now, if we try the more stringent PMV target, you can see that for 77 to 80%, 85% of the time, we meet that target. And this is assuming that the airspeed is 0. So we wanted to test it during still conditions and during windy conditions. And you can see here, there's a bit here that is too hot. So what we wanted to see, well, what if the wind speed was 1.2 meters per second? And you can see that shifts the comfort zone towards here. So that part becomes covered in comfort. But at the same time, that makes these temperatures too cold. So that means if it's really, really windy and the temperature is not high enough, you will feel cold. So what we believe
when
is
you say you mean people who are adapted,
Yes.
physiologically adapted to that climate.
Yes, exactly.
Not people like me.
Yeah.
That was really comfortable.
Yeah, because 25 degrees would not be considered cold here, I guess, in any context. But so what we believe is that, oops, where is it? This one. What we believe is that if we give the occupant control over that wind speed, we can use both of them. We can expand it. But that means that the occupant has to be able, when it's very windy, that they can close the shutters. They can close that draft. And when it's not windy, for example, that they can use a fan.
Just elaborate on that control of the window airflows. So the best solution they're not fitted yet, was Venetian blinds.
Mm-hmm. Yeah. So if we do that, the comfort reaches 99 to 100% of the time, just by changing the wind speed. That's all we have to change. So can that be achieved by fans? So I looked at a few studies, and you can see fans can reach up to 2 meters per second with the wind speed. But the problem is, look at how they project. You have to be directly under the fan to get that 2 meters. Just in this area, it's 0.4. So that is one of the limitations of fans, and that's why it's really key to design the fans to be where the occupants are.
But there are two aspects here, right? One is in the communal areas, in the living areas, you may not be under a fan, but in a bedroom, the fan is placed over your bed, so actually
it's quite small.
Yeah.
And fans can alleviate 3 to 4 degrees, which is mostly agreed on, but some studies go up to 10% of how much they alleviate. But this is a key part, that the temperature has to be below 32 degrees. Why 32? 32 is the temperature of your skin. If the air that you're blowing through someone is 33 degrees, you won't get that benefit of helping sweating, because that air is hotter than the person themselves. So Andy is going to talk a bit about his experience on a particular day.
So we were over there, me and Kamran were over there on a particular day in May, and I decided to spend the night in order to personally experience it and try to calibrate the measurements against my own experience. We had an anemometer, where I was also trying to capture wind speeds outside and wind speeds inside, which was basically ridiculous because I had to take a reading outside and run in, by which time the gust had gone, so it wasn't very effective. But I started to get a sense of what a particular breeze in the building felt like, and I could take a reading. So what was a comfortable breeze from outside coming through the building was about 1.5, was a nice gust that came through the building. Quite often it was 0, and that was when it became very still. So it's quite a good bit of weather to test. So I found that basically it was uncomfortable outside, and I found it adequately comfortable inside on this particular day. I had a good night's sleep. I had the fan on for a short period of time, but I found I could turn it off about midnight. So that sort of personal experience with the data, with the modelling and so on, was invaluable. Actually, I would like to go and spend longer over there on that basis, get a really deep understanding of what we're doing. Sorry? We oriented the building for maximum shading, so it was east-west. The narrow elevations were east-west. The predominant wind direction was from the east, which I think is probably less important, actually. We were thinking about that. But the main thing was that most of the elevations did not get sun because of the overshading roof. The east elevation did get sun. We were going to shade that elevation. At the moment, we haven't done that, and I think we are noticing that impacts those end bedrooms because of the heating of the rockwork, even though it's white, painted white.
Yep. So achieving 1.5 meters inside a building is a huge achievement. It just shows you that we can get good wind speeds without a fan, but we need to make sure that they have access to that fan as well. So these are our future developments. First of all, we want to optimize the fan design by utilizing movable ones. So that gives the occupants more options. If you're in the living room and you're not directly under the fan, you can use a movable one. But obviously a movable fan is smaller, so you won't achieve that 2 meters per second. But if you locate it close to you, you can achieve that level of comfort. What's important is that we've shown that the temperatures in our building can be comfortable with just a fan. You don't need an air conditioner. But with that in mind, we are looking at future-proofing the designs for the bedrooms by adding air conditioner there. Now, why is that? It's because climate change is happening, temperatures are getting higher, but also, as I mentioned in that question earlier, that with economic development, people do install air conditioners, and if you don't plan for it, they're going to do it without planning. They're just going to install it. And this is a building that relies entirely on natural ventilation. If you just install that air conditioner, they're going to think, oh, we're going to need to close up all these openings. And once they do that, that building will only function as an air-conditioned building. You've lost that natural feature. So what we're trying to do is to find a smart way to incorporate that air conditioner so that they can use it when they need, when it's really hot, but also when the temperatures are milder, that they can still use that natural ventilation. So it's marrying the two, making sure they have access to both. And we also want to look at utilizing the site design for improved wind flow and shade to use what we have in the surrounding area.
And it's worth elaborating on that, because the test unit was in a more wooded area, and it is cooler there. It is cooler in those treed areas. This site was very open, not even ground vegetation, mainly sand. So I think we have got one data logger I've remembered is in that wooded area. So we'll be able to compare already last year's temperature versus ambient temperatures, just to try to get a sense of, yeah, you can see there it's sort of very, very exposed.
Find this site. Here it is.
So I imagine that by planting trees, fast-growing trees around the building, we're going to get a significant cooling effect.
Yeah.
But
so
it will take time for them to mature.
So this is the test unit, and
Yes.
it's very woody over here, but this is a bit more open, so there's
Yeah.
windfall. Because we have to be strategic with those trees. They provide shade, yes, but they might block the wind flow. So you have to design them in a way to make sure that you achieve both, in a sense.
And what we're hoping is that these will become rules of thumb, so that we can apply, simplified design codes that might allow this type of approach to be applied to somebody's house, locally.
Okay, let's go back. Wrong way. Yeah, that's the end. So, do you guys have any questions? Yeah.
One question.
Yeah.
You first, and then
Sure.
you.
Would you consider changing the